We want to talk about gravitational attraction as it was described by Newton, and that was a great breakthrough in his time. Here's his universal law of gravity. It involves the force of gravitational attraction. It says that that's equal to some constant, some universal gravitational constant that Newton didn't have a value for in his lifetime, but he knew that there was a constant there, multiplied by the mass of object 1, multiplied by the mass of object 2, and divided by their distance, the distance between their centers, squared. So this force of gravitational attraction is directly proportional to the mass of to the product of the masses. That means if I keep mass 2 the same but double mass 1, I've doubled the force. If I keep mass 1 the same, let's say, and triple mass 2, I've tripled the force. But if I double mass 1 and triple mass 2, then there's 6 times the force of gravitational attraction. That's assuming the distance stayed the same. Now, the relationship between the force and the distance is that the force gets weaker as the distance gets bigger. So if I double the distance, I'm going to square a factor of 2. So the force is going to become 1/4 as strong. And if I triple the distance from the original, then I will be dividing, my whole formula will be divided by a factor of 9. So the force will be 1/9 as strong just because I tripled the distance between the two objects. And that assumes that the masses were staying the same for those two objects. I have a fun little question here. Speaking in all gravity, to whom is the guy in the middle more attracted? Is he more attracted to the guy on the left or the girl on the right? Well, we point out that we've listed the masses for these people, and so we're going to apply Newton's law of gravity. Here we put in the gravitational constant. That universal gravitational constant was figured out using a torsion balance device that was developed by Henry Cavendish. And so in his lifetime they came up with the number for the universal gravitational constant. That is now an accepted value, and it's been measured more and more precisely throughout the years. So now we have a very precise fix on it, probably more than 3 significant figures, but that's all we're using in our formula. We see the force of attraction between the guy on the left and the middle guy is the product of their masses, and is divided by the distance between their centers squared. So we have 95 kilograms for the guy in the middle, we have 182 kilograms for the guy on the left. Multiply those together, multiply it by 6.67 times 10 minus 11th, divide that by 2 squared, and we'll get the force of attraction of the guy on the left for the guy in the middle, or you can say it the force of attraction of the guy in the middle for the guy on the left. So that turns out to be 2.88 times 10 to the minus 7 newtons. We did the same thing over here to calculate the force of attraction between the guy in the middle and the girl on the right. We still use the universal gravitational constant, multiply it by the mass of the guy in the middle and by the mass of the girl on the right, and divide by the distance between their centers, and we get this number, 7.92 times 10 to the minus 8th newtons. Now, at first blush, it may look as if 7.92 is bigger than 2.88. It is, but it's multiplied by a different factor, 10 raised to a different power. So I put these out, I wrote this out in standard notation, not scientific notation, so you could see that 792, what is that? That's 79.2 billionths of a newton over here, and this is 288 billionths of a newton over here. So this 2.88 times 10 to the minus 7th is actually a bigger number than 7.92 times 10 to the minus 8th. And so the guy in the middle, we find out, is more attracted to the guy on the left than he is to the girl on the right. Well, by how many more times is he attracted to the guy than to the girl? That's not too hard to figure out. We say the force of attraction between the guy in the middle and the guy on the left is 2.88 times 10 to the minus 7 newtons, as we showed before, and you divide that by the force of attraction to the girl on the right, 7.92 times 10 to the minus 8 newtons, and you get a factor of 3.64, saying he's 3.64 times more attracted, or more strongly attracted, to the guy than to the girl. Well, an interesting fact here is that the the mass of the guy is separated from him by 2 meters. The girl is separated from him by 2 meters. So if everything else is the same, all that's changed is this guy on the left has more mass and the girl on the right has less mass. And so if we divide their 182 kilograms of the guy on the left by the 50 kilograms of the girl on the right, that factor is also 3.64. And so this is bringing home the point that the force of gravitational attraction is directly related to the force to the masses of the object. We had, if you compare the force of attraction of the guy in the middle to the girl to the force of attraction of the guy in the middle to the guy on the left, you'll see that the ratio of the masses of the guy on the left and the girl on the right is responsible for, according to Newton's law of gravity, is responsible for the change in that gravitational attraction. It's directly proportional. The ratio of the forces of attraction is directly proportional to the ratio of their masses. Okay. Here's a different question. Now, instead of asking about the force of attraction between the middle guy and either of the other two people, let's ask what is the force of attraction between the guy on the left and the girl on the right. And a simple one way to work this, I'm going to show you 3 of them, is to plug in. The first way is easily to plug in simply to plug in the values that we know into Newton's universal law of gravity. So we have G. We have the mass of the guy on the left, the mass of the girl on the right. And now we show that they're actually 4 meters apart, which they have been all along. So we plug all those values in, we get 3.79 times 10 to the minus 8th, keeping 3 significant figures, which is all that's legitimate, since this has 3 sig figs and that has 3 sig figs. We couldn't keep more than 3 sig figs in our answer. Well, let's check out another method. This says multiply the force of attraction between the middle guy and the left guy by a factor that accounts for the switches to information for the girls. That means we already calculated the force of attraction between these two, this guy on the left and the guy in the middle. But if I switch out the information for the girl instead of the information for the guy in the middle, then we should be able to get the same force of attraction between the guy on the left and the girl on the right. So here's the force of attraction that we did have between the guy in the middle and the guy on the left, and we're going to multiply it by a factor that accounts for the changes in information between what we had for the guy and what we have for the girl. Well, here's that factor. That factor, it's like taking Newton's universal law of gravity and putting in fractions for the before and after. Or actually for the after and the before. Okay, the gravitational constant never changes, so that's gonna cancel out, and the mass of the guy on the left never changes, so that's gonna cancel out. We'll cancel those two things out, but we have this fraction for the mass 1, and here we have the girl's mass on top, which is the after situation, and the guy in the middle, his mass for situation 1. So we have the before and the after situation there. The after and the before. The after divided by the before. Also, we have a change in the displacement, the distance between their centers. 4 meters is the distance between the girl on the right and the guy on the left, and 2 meters was the distance between the guy in the middle and the guy on the left. So we did take that factor into account. That factor turns out to be, if you put it in your calculator, if you take 50 divided by 95 and divide that by parentheses 4 divided by 2 end of parentheses squared, you'll get this 0.131. Actually, it's probably like 5 nines and a whole bunch of decimals. I've kept 4 sig figs, even though we're only going to get to keep 3 in our final answer. When you multiply those out, voila, you get 3.79 times 10 to the minus 8 newtons, just like we did on the last page, right? On our last example, plugging everything straight into Newton's universal law of gravity, we've got 3.79 times 10 to the minus 8 newtons for the attraction between the guy on the left and the girl on the right.